Example vector Huffman code. Symbol probability code. Symbol AA probability 4 by 9 code 1. Symbol AB probability 1 by 9 code 011. Symbol AC probability 1 by 9 code 0101. Symbol BA probability 2 by 9 code 0100. Symbol BB probability 1 by 36 code 00111. Symbol PC probability 1 by 36 code 00110. Symbol CA probability 1 by 9 code 000. CV symbol probability 1 by 36 code 00101. Symbol CC probability 1 by 36 code 00100. L average equal to 1.27 bits per symbol. Disadvantages of Huffman code. Here, this average is 1.27 bits per symbol. Okay. Disadvantage of Huffman code. For large alphabet size, M requires large calculations. Requires knowledge of probabilities. Disadvantage of Huffman code. Coding tables also needed to be sent. JBEG, MBEG, etc. have defaulted Huffman coding tables. Some other coding schemes: arithmetic coding, Goulomb and Goulomb rice coding, Lempel, ZIV, Welch, LZW coding, run length coding, predictive coding, run length coding. Identical consecutive symbol values are called runs. Identical consecutive symbol values are called runs. A run length pair indicates value of new intensity and run length, most useful for binary images. 1D run length coding, one dimension run length coding. Assume that first intensity is always 1, run length may be 0. Alternate code words indicate runs of 1 and 0s. A special code indicates end of line, EOL, end of line. Run lengths are Huffman coded, and runs of 1 and 0s may use different Huffman codes. 2-dimension 2D run length codes uses relative address relative to previous line. For first line, previous line is assumed to be all ones. Bit plain coding, symbol based coding, bit plain coding. Bit plain coding, images with more than 2 intensities can be coded using bit plain coding. An image with m bit intensity value can be considered as a composed of m binary images by taking bits with the same weightages. Intensities are generally gray coded. PMT uses run length coding, symbol based coding. An image is represented as collection of frequently occurring sub-images called tokens or symbols. Each symbol is stored in a dictionary. An image is coded as sequence of triplets. First two codes give position information, and the third code gives location in dictionary. Figure 8.19, a 256-bit monochrome image B2H The four most significant binary and gray coded bit planes of the image, all bits. Here A7 G7, here A6 G6, A5 G5, A4 G4. A, figure B, figure C. A bit level document, symbol, a bit level document, symbol dictionary, token 0, 1, 2, symbol for token 0, for token 1 this is the symbol, for token 2 this is the symbol. The triplets used to locate the symbols in the document. The triplets used to locate the symbols in the document. Triplet 0, 2, 0, 3, 10, 1, 3, 18, 2, 3, 26, 1, 3, 34, 2, 3, 42, 1. Predictive coding similar to TBCM. Predictive coding. Current pixel value can be predicted from neighboring pixels. Prediction error has non-uniform distribution near 0 and can be specified with less number of bits. Prediction can be based on current line one-dimensional prediction or based on current previous line 2D two-dimensional prediction. In video coding motion, compensated residuals are coded, giving large compression ratio. Prediction can be done using various criteria like near minimum mean squared error, like linear minimum mean square error, LMMSE criteria or least square criteria. Here this is the input, predictor, quantizer, symbol encoder, compressed image. Input, predictor given to quantizer given to this adder given to symbol encoder, then compressed image. Then here also straight input going, so adding these both, then getting symbol encoder, compressed image. Here input, symbol decoder, adding symbol encoder, then predictor, quantizer. This is adding these two, symbol decoder and predictor quantizer connected to decompressed image. Then this feedback connected to negative feedback predictor quantizer. This predictor quantizer output connected to this adder. This adder getting symbol decoder from input and then predictor quantizer, then getting decompressed image. So this is the difference for compressed image, decompressed image. Here for decompressed using this one part, symbol decoder, predictor quantizer, input. For compressed image, input, symbol encoder, predictor quantizer, then getting compressed image. Transform coding. Coding, how transforming? Lossless image. No loss in this image compression has generally small values. For large compression, we go for lossy compression. Block diagram of transform based compression is shown below. This is the important for small values. We are going to lossless image compression. For large compression, we are going for lossy compression. Okay, for a large value. block diagram symbol diagram of transform based compression is shown below. Input image, transformer, quantizer, encoder, compressor, compressed image. That is input image giving to transformer, transformer output giving to quantizer, quantizer output going to encoder, encoder output coming to as compressed image. Example using 2D 2-dimension TCT. Image block 128. Image block 128. Example using 2-dimension 2D TCT. 2D TCT of the block. Low coefficients are bigger than high coefficients. Low coefficients are higher than high coefficients. Here, these negative are low. These positive. These are high. These negative. These all are negative. These all are okay. These all are negative. Low. Negative means here low. High is positive. Okay. Examples using 2D DCT normalization matrix. Example using 2-dimension 2D DCT. QDCT of I comma j equal to round of DCT of ij divided by n of ij. Only 19 out of 64 remain non-zero. Only 19 out of 64 remain non-zero. Example using 2D 2-dimensional DCT zigzag scanning pattern. Example using 2D DCT run length symbol representation code equal to run length symbol representation code 2 of 0, 5, 0, 9, 0, 14, 0, 1, 1, minus 2, 0, minus 1, 0, 1, 0, 3, 0, 2, 0, minus 1, 0, minus 1, 0, 2, 1 minus 1, 2, minus 1, 0, minus 1, 4, minus 1, 0, minus 1, 0, 1 EOB. This is Huffman coded using coding tables. Compression of the order of 6 is obtained. Figure A, B, C, D, E, F. Approximations of figure 8.9 A using DCT and normalization array of figure 8.3 B. A is that A is using DCT normalization array. This is DCT normalization array. A is the Z. Okay. B is the 2Z. C is the 4Z. D is the 8Z. D, E is the 16Z. F is the 32Z. So 32Z is better. 16 is Z is better. That is Z is better